I get tired. Hello, everyone. Welcome to the August Python Meetup. As you can tell, if you've been here before, Ferris is not here this month. So Walter, David, and I are kind of co-hosting, co-emceeing this whole thing. So please bear with us. Okay, start with this Wi-Fi info. We're also live streaming. And the first item on the general agenda is please be patient. Well, I guess the space is not that new.
Yeah, we're not really setting up in the space. Well, I am, but...
But please be patient with us as we figure out what we're doing. So SLC Python, we've been in existence for what,
2014.
Yeah, if anyone knows the history, you're
welcome to take over, because even though it's repeated every time, I still don't have it memorized.
Ferris and I started this group in, I think, February 2014. Yep. So.
At a coffee shop, right?
At a coffee shop.
All around Django.
Yeah. Sugar
me and this other dude were working on a Django app. Ferris came up to us. We started driving on Django. Then we figured that we didn't want to drive to Point of the Mountain for the existing Python meetup, so we thought we'd take matters into our own hands and start our own meetup. So we started this meetup, and here we are, 1,400 members later.
Yeah.
What? It's crazy. Okay.
I don't know how we fit all of you guys in here.
I know, right? The city's definitely a big group, I guess. So,
yeah. Some people are only here in spirit. So then we have Salt Lake City, the Utah Python. So Utah North, they meet in Logan, is that right?
Yeah, they
so,
meet
yeah.
in Logan.
Yeah.
And do we have any Python Utah Python North people here tonight?
Usually we
Nope.
do. I guess not.
No.
We see everyone.
Yeah.
They'll be back next month, I'm sure.
Now we have Salt Lake Pie Ladies.
You go to that. You wanna...
Yeah, we have it. We're not meeting necessarily every month. It's more ad hoc, I would say, probably every other month more so. But anyone's welcome to come and join and check it out, and always looking for new members and people who have interesting things to present as well. So you can just check us out on Meetup. And we have Python at the Point, which is down south, and Provo. So Provo and Python at the Point are now the same thing,
Yes.
I guess.
I think they're meeting now during the daytime. Is anyone from that group?
I've gone to it a few times.
Have they switched it over?
It's a lunch
Lunch
thing.
hour one? Yeah.
Interesting.
It's too far away.
Yeah, I'm never going down there. Girl Develop It, that's more general purpose, focused of course on female membership, but it's not only Python, it's a lot of different programming languages. We meet once a month. I believe it's the third Wednesday of the month. Cool. Then we have our websites up here and GitHub repos and our sponsors, Pythonistas like you. Thank you for your donation. If you still have money to give or would like to make a donation, Walter has the square to take cards. I will take cash. Thank you. X-Mission and also the University of Utah, they're hosting the venue here. And
Do we have
that
any,
is with X-Mission.
sorry to interrupt.
Yeah.
Do we have any messages from X-Mission this month?
Dropping the Python, we use it. So
Awesome.
Nice.
it's the best.
Nice. And of course, new sponsors are always appreciated. If you ever want to look up information about our past expenses and sponsorship,
It might be 2 months out of date. with Ferris
Except
being
July.
except for July and August. Ferris has been a little busy, but transparency is important. So, except for July and August, if it was anyone's game.
It'll end up
Hopefully
there
everything
eventually.
else
It
is
just won't be there right
transparent.
now.
So yeah, if you ever want to look it up, just see where the money is going to and how your donations are using. If you could.
It'll show up though. You can.
Oh yeah, I can show them the statement.
Anyway.
Sorry.
Our new members. So who's new tonight? It's your first time? One, two. Okay. Cool.
All right.
So
Presentation.
that's awesome. We always go around with the new members and say name, occupation, and favorite Python package. So I think I'll have you over here. Just tell the group your name.
We typically just
what
stand
you
up.
do, just stand up.
Just a brief
Or that real
intro.
quick and then pick the next
Just
person.
brief intro. So it's just like who you are, what you do, and we always have a little bit of a question. So today's icebreaker is your favorite Python package.
So I'm Daniel. I work in the UOnline / Teaching and Learning Technology Center here at the U.
Okay.
And my favorite Python package is probably Pandas right now.
Nice. Cool.
And then you get to pick the
When
next.
new people, hands up,
Who's
So
next?
raise your hands for
Raise
who's
your
next.
hand.
and then choose somebody.
My name's Ryan Taylor. I work at the NanoFab on campus and do random software stuff for them. And Python package. I like requests, I guess, is a good one.
Oh, request is good, yeah.
Okay, who's next?
You want to go?
You drag me along.
Mr. Plus One.
I don't have a favorite package because I don't know that much about it. I just work at the library, in the digital library, the less technical side of things, and I'm just trying to learn more about how I can use this in my.
Welcome. You come to the right place.
Yeah.
Cool.
And pick somebody,
Who's next?
one of the new people. There you go.
My name's Justin Holtham. I work at Sorensen Media and their NOC and sort of help with the DevOps stuff. And I don't have a favorite Python package because I just started learning.
All right.
Cool.
Nice.
Oh, we've got to start somewhere.
If you raise your hand so you can thank you.
My name is Carol. I'm a security analyst for a mobile network operator, and I've been creatively plagiarizing Python for a while, and I'd like to create my own.
Welcome. Okay. I'll just call on you.
Adam Jackman, I work for a small startup, just kind of doing computers, so end-to-end, full stack. I really like requests because it makes life easy to just plug duct tape APIs together.
I'm Garrett. I work as a bioinformatics developer. My background is more in the bio and just kind of more getting started with the informatics part. But my favorite Python package is PySam. It's a kind of a biology specific one.
Oh, nice.
Any others?
Okay, have we missed anyone? Joe's just pointing people at us. You can't get away.
My name is Farmas Safazadeh. I'm a PhD student at civil engineering. Last semester I had to do around some numerical simulations and I had to use Python. So I'm barely new. I don't know about the packages.
Okay, cool.
Welcome.
So Joe might have an eidetic memory, so he's been on Jeopardy.
What's
This
this?
is like to mention.
I was like, there's a couple more.
Hi everybody, my name is Binu. I'm a PhD student at the School of Computing at the U. And we do use a lot of Python in our research group. My research is focused on floating point error estimation and precision tuning. My favorite package is NumPy.
Nice.
Thanks.
All right.
Anyone
Joe, have we fully
else?
exhausted
First
everyone?
time?
I think so.
Yeah. You're not missing them all? Okay.
Okay.
What's next?
Who's hiring?
Oh, the who's hiring and who's looking. This is the fun part. So, who's hiring?
You want to put
Who has
type
jobs?
those
So my name's Eric Hurst. I work at Team, and we are looking for full stack engineers, either front end or back end.
Wait, if you're front end or back end, how are you full stack?
Right. So we're looking for good engineers. That's what we're looking for, right? We're looking for all around good people, and obviously in this group, probably more back end people. We have openings for both positions. I know we have positions on our data team to do kind of some data visualization, as well as working on our kind of main administration website, as well as doing some integrations with other cool technologies like Alexa, that kind of stuff. So again, team, and if you are interested at all, come and talk to me afterwards.
Thanks.
Anyone else?
Wow.
What?
It's pretty dry.
Usually.
Dry month.
Usually there's
Anyone want to
some
fabricate a
people.
job just on the spot?
Entrepreneur.
Don't work for free, I've got plenty.
Oh.
All right, so who's looking?
Intern, yeah, who's looking? Anyone want to sell their skills?
No one's
Everyone's
looking.
happy at their current job.
Cool.
The negative unemployment rate now technically. So.
Still qualified.
Still qualified.
Oh, we didn't actually list any community news. Does anyone know of any community
is there
news?
any?
I don't. No? Okay.
away.
So, moving right along. These are our list of topics. You can find the link to this. Excuse me.
Oh, I forgot.
I am taking over for you. Carry on.
You're fine. You're fine. I was okay with that happening. Yes, you can. You're saying you can find the link up here.
Yeah.
And contribute if you want.
And for those of you who were expecting the panel, I apologize. Things got a little confused there at the end, but we did add that to the list, so hopefully we will be doing that talk in the future.
Yeah.
Soon.
So basically, if you have any ideas for topics, if you have something you want to talk about and share with the group, that would be awesome. And just either put it up here or let any of us know, and we'll get it on the schedule probably pretty soon. So.
And we need a break.
Yeah, we'll take a quick break, get Eric set up. He'll be presenting on Python under the hood. So,
5 minutes?
5 minutes.
Yeah.
Sound good? Awesome.
Cool.
Well, I guess I can stop the stream and then start it again, right? Oh wait, that'll make a separate stream.
Yeah, just leave it go.
Maybe I can just mute it.
Everyone?
Do we want dim the lights or do we want
Yeah. Mood lighting or no?
Yeah, definitely.
Good night, everybody.
I mean, it's our curse. We can figure out
Pretty good? He's ugly, so dim the lights. Thanks, Joe.
I didn't imply that. You did.
We'll switch to the camera for a second.
Okay, awesome. This is just kind of a little introductory XKC article. Obviously, you can't take a course where the prerequisite is that course. It's going to kind of fit into what we're going to talk about. So Python under hood, or CPython demystified. That's going to be what we're talking about. A lot of us have used Python, whether a lot or a little, but I would venture to say very few of us know exactly how Python takes our code and runs it in a computer. And that's what we're going to kind of talk about, how it gets from Python to being zeros and ones. So first a little bit about me. As I mentioned before, I am from Team. My name is Eric Hurst. I work directly with Ferris, so I know a lot of you know Ferris. And if I would say anyone's my arch nemesis, it would be Joe. We used to work with him.
Oh, you're supposed to boo, right?
And he used to sit across from you.
I used to be your boss.
Basically. Then you betrayed us. Anyways. So I graduated from the University of Utah in around 2014. I've been doing Python work more or less since then, whether it was just like as a side, just a tool to use in order to do other stuff, or actual web development where Python was the main language. I've worked at SanDisk, or Fusion.io, if you remember, way back, and there I did more embedded programming. It's kind of lower level, C-level programming. From there, I decided to switch and do more web development. That's when I switched to Team, which was Eventboard at the time. I joined Joe's team and doing a little more data stuff, more data-driven visualization. Since then, I've kind of moved towards more general web development and kind of leading a team to create new features for our customers. And so we are hiring, of course, and we are on the way to really cool and exciting things. So I more than encourage anyone to kind of apply and talk to me afterwards. Anything else about me? So I want to start off kind of with a history story about computer scientists and computer programmers in general. In the beginning, there was assembly code. People wrote assembly code all day. There was a lot of it. There were various types of assembly code that compiled down to very different processors. There are many different colleges who are using very different styles of assembly, different ways of writing programs, and in general is messy because there's a new field. People are still kind of figuring it out. Eventually, people started to notice patterns in how they're writing assembly code. And it started to get repetitive. And us as programmers, we're very lazy, and we don't like to do extra work that we don't have to. And so people wrote programs to write code for them, and thus compilers were born. So compilers are, a method of taking a simple program like this, very basic, most basic you can get C program, and turn it into assembly code. And this is the actual assembly code that is generated from just this 3-line program. So you can see it saved quite a bit of time, and it saved quite a bit of repetition. Now as people started writing more and more in C, they started noticing more and more patterns. They didn't like managing their own memories, so they wrote yet another language which did more stuff for them. And thus the cycle continued where people wrote more and more advanced compilers and languages in order to express what they wanted the computer to do. But why should we care? Why do we care what other people have done? No one, I'll make the assumption not many people here write in assembly every day. If you are, then you're in a very specialized field, because no one really should be writing assembly these days because compilers do all the work for us. However, it is very useful to know where we've come from and how compilers work, so that we can, know how to best communicate with the computer. So I want to, and I'm getting to Python, so don't worry.
Surprise!
Surprise! Python. I consider code a language, and we often call programming languages, right? They're called languages because they're a way of communicating, and they're special in the way that, unlike spoken languages, we're communicating in between people. Programming languages are ways that we can communicate with the computer. It's how we talk with the computer and tell it what to do. And so learning to code is just like learning another language. How many people in here are bilingual or know a different language? All right. How many people have done like translation services or done professional translating in between those languages? All right. Yeah, I haven't either. I mean, it's from what I've heard, it's really hard to do. And so that's where compilers come in. I compare a compiler to a translator. So a translator comes in, takes your language, translates it to another language that the other party understands. This is exactly what a compiler does. It takes your code that's all nicely formatted and very pretty, turns it into a mess of ones and zeros that the computer can understand perfectly, so that we know it could we understand. Sweet. So the more you know, the lesson is the more you know how this stuff works, the better you can be at your job, the better you can write Python code, the better you can reason about what you're doing and telling the computer what to do. And so that's kind of the basis for this presentation, is to understand Python under the hood and at its base level, so we can know what it's doing and we can better utilize it in our daily jobs. And my strategy here is to kind of introduce it at a high level so as not to scare anyone away, but also to kind of open the doors for you to explore on your own if you'd like to. I'm by no means the world expert on Python, but I do know a little bit, and I'd like to share that a little bit with you today. So I have a question. I want to open it up. I don't like to talk a lot, so I want to hear from you guys. Is Python an interpreted or a compiled language? Who can answer that?
It's both.
Good. Why?
The code that you write gets interpreted into the PyC files. That's why I know.
Okay. So what does interpreted mean? Can someone can they answer that for me? Or what does compiled mean?
You should make your nemesis answer that.
It doesn't exist.
So compilation is like that translation step. Interpretation is saying, okay, we're not really quite at those ones and zeros yet. We have a Python interpreter that picks up whatever that Python bytecode is and turns it into the ones and zeros dynamically.
Yeah, absolutely. So you can probably compare compilation and interpolation to compiling is like putting everything into a book, and it's all there ready for you to go. Interpretation is kind of like someone speaking, and an interpreter will interpret as it goes. And so an interpreter kind of runs the program and reads the code kind of as it goes along and compiles all along the way. On compilation, you compile all beforehand and the machine just runs it. And so the gentleman in the back is right. Python is both. It has both a compilation step and an interpretation step, and we'll kind of get more into that later. And thus comes into play C Python. Who's heard of C Python before? Good. C Python is the kind of standard Python implementation. So Python in itself is not a compiler or interpreter. Python is a specification of how code should look and how code should run. It's up to implementers like CPython to kind of take that specification, write a program which actually does the things. CPython is maintained by the maintainers of Python, and it is the reference implementation. So it is the most used implementation of Python. There are other implementations of Python in various different formats. There's PyPy, which is another C version of Python. So CPython is named because it's written in C. PyPy is another C version, which is supposedly faster, but it has limited. It's a little more limited in what it can do. Jython is a Java implementation, so it will take your Python program, compile it into a Java jar, and be able to run, and you'll be able to run it like Java. Iron Python, I forget which this one is. Windows? Oh yeah, .NET runtime. So you can run it on .NET runtime. Py.js, compile Python to JavaScript. Cython, compile Python directly to C instead of going through kind of this interpretation step. And Pythran was an interesting one, and I forget what it was already. That's unfortunate.
Fortran? Yeah, it's Fortran, but
I'm just guessing.
It's not really widely known. I remember it wasn't very popular, but I thought it was interesting. Anyways, I'll have to look that up.
It's a C++ compiler.
Oh yeah, that's right.
Okay.
It takes it to C++, which I don't know why anyone would want to do that. I'm not a proponent of C++.
Makes more sense than JavaScript.
That's true. I mean, at least if it's JavaScript, you can run it on the web. The C++, it's just a mess. All right. So I'd like to take you kind of through what it takes for Python to be a piece of code down to running that code in the computer. And I've broken down to kind of, it has 4 steps or 3 transformation steps from 4 different things. So first, it starts out source code. That's what you write. That's what we're all familiar with. Again, it gets parsed into an abstract syntax tree, and we'll cover all these more depth in a little bit. And that's where the compile step comes in. That's where Python is compiled into bytecode, and then bytecode is then interpreted when you actually run your program. So first, source code. We're all familiar with Python. It looks pretty. That's one of the reasons I love Python, is it looks nice. And it's very easy to read. And that's one of the benefits of having compilers, is that we can write something that is easy to read for us, easy to reason about, but then the computer can still read it. So then this will go through what's called a parsing step and get transformed into an abstract syntax tree. Now, I don't expect you to understand everything here, but know that that Python program, which was so this example will find a prime number. It's taking in 407, and will print 407 is a prime number or is not a prime number. It's just an example I pulled off the web. And we're actually going to go through each step and actually see the representation at each step. So this is a tree structure representing that program. Each node is kind of a syntactical element of the program. So all the if statements are represented in there, all the function calls, all the function names, all the function calls. They're all represented in kind of this abstract way, representing the syntax, and it's in a very tree-like structure. That's why they call it an abstract syntax tree, or AST for short. We do this, you don't usually see it that often, but we do this because it makes it so much easier to reason about the program we're doing. And from here we can do a bunch of transformations on this tree that will optimize your code, that will prune out code that doesn't need or ever run to make it faster, and do whatever it needs to do. This will then get compiled into what's called bytecode. Now, in Python, this is the .pyc file that you see. This is a visual representation of that file, of that PYC file. Now, obviously, the .pyc file, for those of you who don't know, when you run a Python program or a Python file, for example, example.py, when you run it the first time, you'll see another file pop up next to it, which is the example.pyc file. That's the compiled version of your program. And so Python does that for you without you even knowing it. And this is kind of what the bytecode represents. So yeah, go ahead. Sorry.
So when you're at the bytecode level, is that basically the calls to the underlying C code? Is that what bytecode is? Or is that a nonsense question?
No, it's a good question. We'll dive deeper into it. We're actually going to we're going to explore the C code of the C Python compiler, and we'll see where these come into play. But this bytecode is explicitly a version of Python bytecode. So there's a spec in CPython that defines what these all mean, and then they get interpreted by and run in C. So a C program will take this in and run it. And so here in the bytecode, you see it's just a sequence of instructions. There's no branches, there's no for statements, except they're kind of embedded if you look at them. If you look at it closely. And we will explore that a little bit later. We'll kind of go in more depth onto how the kind of the bytecode works, or how to reason about it. But when CPython gets that PYC file, it knows how to run it, and it outputs the output. So we see 407 is not a prime number. 11 times 37 is 407. Are there any questions at this point? Any comments? Did I lose anyone in the weeds? I'm more than happy to answer any questions. Please speak up if you do. I like to be a little more interactive. So let's explore CPython a bit. CPython is as easy to get as just cloning a GitHub repository. It's all in, we'll open it up right now. This is literally Python here. For the longest time, Python for me was like this mysterious program, but here it is, like concrete, here's Python. There's a lot of files in there, but we'll take a look at two of these files, which I deem the most important, and the most important to kind of understand how this C program works. So let's jump into the code. Make this bigger. Is that readable for everyone, especially in the back, or a little bigger? Awesome. So here I am in the CPython repository. Here we see all those same files. First, we will look at the what are called opcodes. So in this is a header file in C. You don't necessarily have to understand how C works or what C even is to kind of understand this. But here we see all the names of the instructions that we saw in the bytecode file. They translate directly into kind of these opcodes. So operation code meaning operation code, right? And we see that each opcode just really represents a number. So that's kind of how CPython translates that compiled Python file, which is just a series of bytes. You can't open up it in a text editor or anything. It will translate each chunk into this kind of instruction and then know what to do with it depending on what instruction it is. So here we can see there's quite a few instructions. Definitely a lot more than you would see in a really low-level assembler, and definitely much more higher level. But nonetheless, it is about 160 different operations that Python handles every time you run Python code. So next, we'll look at the Python/C eval. Let's see. Now this is a big file. There's a lot in it. Well, I'll guide you through it, and I'll show you the most important parts. But basically, all CPython really is a big loop. It's a big while loop that keeps looping until all the instructions are executed. And inside that loop is this is the start of a giant switch statement where it says, what opcode do I have? And if so, jump to that spot to handle that code. And so for me, it was a big kind of realization, realizing like, wow, Python as a kind of thing was very mysterious and kind of how it worked. How does it compile stuff? How does it run stuff? It's kind of interesting to see that all Python really is, a base core is just a very simple loop with a switch statement in it. And I think that's really powerful and really elegant, and that's one of the reasons I'm so interested in compilers and in Python. So if we take a look here, these are all macros to make it much easier to read and see. But each opcode has this target, and so we can kind of go through and see where all these opcodes are handled and processed. And so let's find an example, like binary multiply. So when you write 8 times 3 in Python, this is the code that gets run. This is the code that actually does the actual multiplication of it. Obviously, it's a little more cryptic than just doing multiplication, but what it's doing is Python has an imaginary stack within it for bytecode specifically. Not the stack that you normally think of. But what it does is every time it hits an instruction, it can do one of two things, or even both. It can push a value onto the stack, or it can pop a value from the stack. It can even pop multiple values, it can push multiple values. So all it's doing here is, the first one is a pop, so it's going to pop off the first item on the stack. We're going to assume it's a number at this point because the syntax has already been resolved, and if you had a bad syntax error, it would have errored you out. That top statement is kind of like a pop, but it doesn't take it off, it just kind of looks at it. And then here we see it runs the pi number multiply. That's where it does the actual multiplication of the values. Here we see kind of memory management part of Python. You don't see it here. It's kind of doing the decrements of the reference pointers. And then it replaces that top value with the result. So it kind of pushed onto it. So it kind of reused one of the stacks to kind of improve the efficiency of the multiplication. And then it's done. And that's how all the opcodes are kind of handled. They either push or pop stuff up. And so that's all really CPython does. And that's all really Python is. Are there any questions or anything that someone wants to look at in this file? Anything you're interested in?
So the other implementations that you mentioned, Python, PyPy, all that, are they also all working on the bytecode?
So I believe that they all will have a different, probably a version different kind of bytecode. And a lot of them skip the bytecode altogether. And they'll compile right down to the language, and they'll use a language as kind of the bytecode.
Okay.
So Python, not to be confused with CPython, we'll take the Python code, convert it into C code, and then use a compiler like GCC to convert it into machine bytecode.
Okay.
Which, the machine bytecode is kind of specific to the processor that you're running on. Yeah.
What would be the pros and cons for going directly to C versus going to this bytecode engineering?
Yeah, that's a great question. It's kind of the big debate with Python, right? Python is in many communities deemed slow because it's interpreted, right? And that's very true. Because a simple multiplication statement like this, which is literally one CPU statement in C, is suddenly turned into a multitude of calls accessing a bunch of memory in an interpreted language like this. And so the advantage of compiling directly to C, or compiling C and directly to machine bytecode, is you have a lot less instructions to do kind of the same things. However, having an interpreted language does give you a lot of flexibility, right? And if you're not too concerned about performance, and especially in our day and age where CPUs are so fast that we're not really CPU bound anymore, that flexibility saves you a lot of time in development. And so being able to express what you want the computer to do is much easier. And so that's a kind of trade-off. It's like, do you want speed or do you want to be able to talk to the computer very well? And if anyone has programmed in C, you'll know, or any lower level language, it's much harder to do a lot of things that you can do very simply in Python. So, great question.
Just a quick question. When you were going through this, I noticed like go-to errors. A couple of those. Did you ever look and see where those went? For binary multiply, for example, how does it look it up?
What do you mean, look it up?
Well, because it's just like go-to error,
yeah.
Go-to error for different, I guess, actions. I'm just curious, like, how would it know, like, for binary multiply, what error it would?
No, gotcha.
Right.
So in C, a go-to statement it goes to a certain point in the code. So let's go there. So it will literally in the program just stop whatever it's doing and jump to this part of the code and start running. And so if we take a look at this, here we see it asserts y and why not. Interesting. Y is equal to y exception. And it will run a function that says, did a pi error occur? And if it did, then hey, do something about it. Now I assume that what it's doing is, and I've seen this in a bunch of other languages, it will set a global kind of error variable. When it's going through and it hits an error, it'll set that to true, and so when it comes back out, it can just go to the error statement, and then the error handling will look at that and say, okay, what happened? And then it will execute. And they do that for speed in C.
Is that Y exception maybe set in the pi multiply if that's called within the binary multiply? Binary multiply?
Sorry, what were you referencing?
So there was that Y exception, Y equals Y exception. Is Y except maybe Y exception is set within the pi number multiply function?
Exactly, yeah.
Is this Python 3 or Python 2?
This is Python 2.7. Python 3 is a little more complicated in its C structure.
I was just surprised to see like the matrix multiply like.
Explain the dictionary comment at the very time.
Actually, no, this actually may be Python 3.6.
Wondering.
And either way, like the difference between Python 2.7 and Python 3.6 is really just the number of opcodes that we see, right? This kind of structure hasn't really changed since the beginning of Python. So the way it's handling it has not changed. So if you look at 2.7 or 3.6, it's going to be pretty similar. Great questions, you guys. I love just jumping around and kind of exploring things. What's up?
So this might be out of scope, but you know, in Python, you usually are interacting with a lot of things other than just like the actual code. So like, does this code handle like opening like a file handle, or is that like happening somewhere else?
Gotcha. So yeah, for kind of higher level things like the open statement in Python, actually that's probably pretty low. It depends. It depends. So as you probably know, that there's the standard library in Python, which is a standard library of modules. While it's not baked into the language, it's still in this repository, the standard library. So what will happen is I think we can take a look. So if we look in lib, yeah, these look like one of the standard libraries, right? Yeah, so you'll find that some of the standard libraries are implemented in Python, and some of them are actually are sometimes also in C, for performance reasons. Which I always find kind of interesting because like you're literally writing a compiler to convert a language to execute but you're writing the compiler in a language that you're writing a compiler for, and so you're like kind of writing yourself. It's kind of like the beginning of Skynet, I feel. So I mean, it's already started. We're already starting writing programs that are writing other programs. They're just not quite intelligent enough yet. And so, if it's really needed for performance, it'll usually be baked right into the code. If it's not, then it's usually in a standard library. Good question.
How does that interface work actually when you have a library that has compiled C code in it? And then I guess the Python part is just a wrapper to access most of that code?
Yeah, and
how's that end up working on the C code level? C code level.
Gotcha. That's a great question.
If I remember right, when you're writing expansion modules or expansions for modules, you include it's a file called python.h, and it says, hey, this C code is supposed to be evaluated in Python, so it'll be past Python things, and then it'll pass its output back to Python.
Yeah, so if we take back a look at C eval, I multiply. What was that?
I know.
High number multiple. Yeah, so take a look back at this. What it's most likely doing, someone can correct me on this, is instead of calling by number multiply, it has a special opcode that says, hey, the user wrote a special C function for this. Here's a function pointer of where it is. And instead of calling by number multiply, it just calls your function. And it just runs your C code, then it returns out here. And if you do, when you do include python.h, you'll see a lot of these functions. You can use most of these functions as if you're in the Python compiler. And many packages like NumPy and Pandas will do most things in C because it's so much faster, and that's why those packages are so popular and so needed for kind of numerical processing, because if you did it in Python, it would be extremely slow. So as an example where you need the speed for the trade-off of flexibility. Great questions, guys. Any other comments before we move on?
So there's this interface of the opcodes, and all of these versions of Python kind of provide the same interface for the opcodes. How do you test that? You just say standard library. Do you do the same thing on all of these? Different, Python and Python, everything else.
So it's like if you're writing your own compiler in, say, Ruby, all right? How do you test it? How do you make sure like it conforms to Python standard? The best way is to compare it to the reference implementation, which is CPython. So that's why it's called the reference implementation. What you do is you take a program, you run it in CPython first to get the output, and then you run that same program in your new interpreter and compare the outputs. If you get the same outputs, that's a good sign. If you get different outputs, it usually means you got a bug somewhere. Great question. Awesome. So with that, I'm glad you guys have a little bit of interest in this. So I kind of want to give you guys some tools to kind of do some of your own exploration. And they're all baked into Python. And so you can use Python to explore Python code. So first, let's open up Python shell. And we'll create a sample function that says hello. And it takes in a name. And we will print hello. And we'll just print hello and whatever the name was. And we'll define that function. What I want to show to you first is a module called dis. So you're going to import dis. Not this, but dis. Right? Okay. Oh yeah, I forgot to close
Yeah,
this.
because you have to double interpret out in.
So we imported this. Right? And dis stands for disassembled. It's a very hacker term to deconstruct code. Find hackers deassembling the code, but it's really just taking the bytecode and bringing it back into something that we can read. And the dis module has a function called dis, and we can give it any Python object, and it will disassemble it for us. So let's disassemble hello. Right. And it will show us, the opcodes that it does when you run the function hello. And so we'll run it from top to bottom. And if you kind of imagine in your head like a stack, First of all, it's going to load a constant, so it's going to load your hello format string onto the top of the stack. It's going to load an attribute, which is most likely, it's the function name that you're going to use to format, and it's load the variable name, and then opcode says call function. And the one next to it is going to be what function that you're going to call. And so it's going to call function 1. It's whatever the computer assigns to it. And that function is going to then pop off and push what it needs to. Most likely this is running the format function. And so it'll push back onto the stack the formatted string. So now after we call a function, all that's left on our stack is our hello Eric as our string. Then there's a special opcode for print. Instead of calling a function, it'll print it. And since when you do print in Python, it also prints a new line. It has a separate opcode for that. And so it'll print a new line. At this point, the string is gone because we printed it off the stack. And now we're going to load a constant, none, and then we're going to return that because the default for a function is to return none. So we can see all the steps that Python goes through just to run this function. And I hope it's not as kind of mysterious as I originally once thought. Suddenly now you can like go down to the bytecode and see exactly what it's doing. And these all pretty much translate to C functions, which will translate to assembly functions. And that's what the computer is kind of doing. It's loading in things in memory and doing stuff, loading it back out to memory. Awesome. Questions about this?
So, what does the second load constant do? Is that making sure that there's nothing in the stack anymore?
Right, so at this point, the stack is empty, right? And you'll see the next one is return value. The function wants to return something. So if the stack is empty, it's gonna want to return the top thing on the stack. But there's nothing on the stack. And so the default in Python is to return the none, which is kind of like the null. And so we'll load that on there and then return that value.
So what are these numbers over here on the left signify?
I believe those are like address is like where they are in the bytecode in this point. So they'll kind of increment.
Oh, is that just from that Python.h header?
The 2 on the side there?
The 0369 set there.
Oh, those ones.
Python.h header, those were just defs.
No. Yeah, so
No,
those.
you see load const gets 2 different numbers there, so I think it's kind of like a number of operations or something like
Yeah,
that.
so that is actually the number of bytes into the bytecode you are.
Okay, that makes sense.
So you'll see between 12 and 13, print item and print new line. Since print item doesn't have a number associated with it, it needs less storage. And it's literally 1 byte just to print an item. And so it doesn't need that much storage, whereas the other ones you need to kind of say, load a constant, but what constant are we going to load? And it has to store that number of which one it's going to load. So it needs more bytes. And you'll see some that are very long, some that are just 1 byte long. Good observation. Nice.
Is there anything that would prevent Python from implementing bytecode, like an eval statement or something within the code that would interrupt that process? Or
I'm not sure I understand.
like if there's something that's causing Python to interpret code or something in the middle of its execution, would that prevent the bytecode from being generated, or would it just generate it on the fly?
So you're talking about like extra code, like in the C code?
Like an eval statement, or
So, like an eval statement in Python will be converted into an opcode itself, I believe.
Okay.
Right, so in many Python scripts, you'll jump out of the script and evaluate something else. There's a couple ways Python could do that. It could spin up another Python process, or it could jump to a special opcode that says, okay, for this, we need to kind of treat it special. We need to parse it down. We need to compile it first, and then run that and go from there. And then wait until it ends and come back to where we were. And we can kind of see that. I mean, Python has quite a few cool functions in it. One is compile. You can literally compile Python code inside of Python. And it's a reserved one, so you don't need to import anything. You can literally compile 1 + 1. Or not. You have to give it a file name. This will be a good time to introduce the AST module, as I was going to go next. So import AST. So Python also has a AST module, abstract syntax tree, to kind of help you reason about other Python code within Python code. And so AST has a parse function, which allows you to pass in 1 + 1. And what it returns to you is a Python object, which is the head of the abstract syntax tree. So that big tree structure we saw earlier, it's going to be a representation of that tree structure. So now you can go through that data structure and reason about it. You can go through and pull all the comments out and figure out what comments are there. You can go in and remove all the comments. You can do a lot of cool stuff with it. And that's how kind of a lot of the testing frameworks will work. They'll go through and they'll look at the AST and say, okay, if it's prefixed with test, I'm going to mark that specially and execute that as a test. So, and all parse is doing is calling compiler under the hood to do that.
If you're interested in playing with that, we Asteroid put out the package Asteroid is put out by the iPlace people, because they have to go through and parse your Python code and say, hey, that's good, that's bad. They work a lot at the AST level.
Gotcha. So Asteroid?
Yeah.
Okay, cool. I know a lot of the recent Python 3.6 type annotations are very similar. They'll have their own AST nodes in the structure, so you can go through and find them, since they are added syntax.
Do those type annotations go all the way down to the bytecode level to see there?
No, those do not. From what I understand of the Python 3.6 spec, is that those are purely informational, and so they don't affect the execution in any way. And so they're only available at the AST level, and then they get kind of ignored when they get compiled down to the bytecode level. And so it's kind of up to the user to inject certain code that you want to verify those types or whatever you want to do with it, so that it gets into the bytecode. Good question.
So will this work on operators, like plus, minus, that sort of thing? Right? You can overload operators, right? So is an operator basically a function? Would you get the same sort of bytecode back?
Let's find out. Let's save this off. If we print it, I believe it will. If we refer it.
Health dir, maybe one of those two?
There was a special. There is a. Yeah, let's. AST entry real quick. I did this before. What was it? Dump. So we can take a look at the AST. Kind of complicated syntax. So if we do AST.dump, AST.parse 1 + 1. So this is kind of the tree representation, we'll see that it's a module, the body of it is an expression, which is a binary operator, where the operation is add. The left one is a number, which is 1, the right one is a number, which is 1. And so that's what it gets compiled down to. It gets compiled into a function call. And essentially in Python, that's what these operators are. They are function calls, right? So in order to do operator overloading, you write a function on an object. And so when Python parses that, it says, okay, what are the types of these two operators? And do they have a corresponding add function? And so if it sees 2 integers, which are built in, it's like, oh, I know what those are. I can add those 2. If it sees like your custom objects, it's like, oh, well, let's check to see if they have an add function there first to find. If they do, okay, replace this with that function call. So yeah, operator overloading is mainly done at the compile level. Yeah.
Python ASTs be used to generate any other language?
I don't see why not. Yeah, that's actually what. Yeah, there's no reason you couldn't. It's literally just a tree, and you just start to, if you just walk the tree and output your own language structure, there you go.
Do you know if anyone's ever tried it?
I'm sure people have, because
there's a few domain-specific languages that have been written in Python that utilize the AST tooling, but aren't necessarily turning Python into other languages.
There was a guy on Talk Python to me 6 months ago or so that wrote his own language in Python. I'm trying to remember.
You talked about that game storytelling thing?
No, I don't think it is. I'll interject when I find it.
Okay, all right, sounds good. Yeah, I mean, the sky's the limit. You certainly could. What was I going to say? A lot of the AST tools are usually made for tooling, so testing, documentation. There's a variety of reasons to use it, including rewriting the code or disassembling the code. You could take Python, turn it into AST, and then write back out Python in kind of the style that you want. So if you don't like someone's style, you just pass it into this and it converts it into your own style, right? Or Pepe it, or if you want, right? Whatever you want to do.
Coconut.
Coconut.
Yeah, this episode 117, for those who are interested. This guy wrote Coconut in Python. It's a functional Python with Coconut.
Okay, gotcha.
It's kind of an interesting episode.
Functional Python. Yeah, sky's the limit. What other fun things can we do? Any other questions for now?
I have a question.
Yeah.
From the sysadmin perspective, if you're running a Python script in a file system that doesn't allow you to write the bytecode, do you end up, I assume you end up recompiling it over and over instead of running the bytecode? Is there an overhead? How much are you saving once you do the initial conversion?
Yeah, that's very interesting. I'm not sure if Python has a way of dealing if you can't write to the file system, whether, you know, it says, oh, I'm trying to run this. I can't write to the file system, I'll just keep it in memory. That'd be cool if it does. I'll try and find that out.
It can definitely run when you don't have write access, when the user
Okay.
doesn't have write access to the directory. I don't
Which
know what it does.
makes sense,
but
yeah. I think it's more of a caching thing
I've
with a
done it.
POIC file. So,
Probably.
in terms of speed, it does vary by program, but generally nowadays, parsing and lexing a program is fairly minimal compared to what you're actually trying to do. And especially if you're doing anything on the network or writing a disk, parsing is going to be, since you only have to do it once, every time you call it, it's going to be pretty measurable. Well, great. I mean, I hope you guys found this useful. I just want to reiterate that Python is not as mysterious as we think, and I hope that it's become a little more friendly. I hope that your understanding of kind of how Python works kind of helps you in your day-to-day, and kind of see how, when you write programs, how the compiler can now optimize it for what the machine is wanting to hear, and all this stuff that really goes on in the background for you when you run a simple Python command. I guess to finish up, I did want to show you that the disassemble module can be run from the command line if you do python n.dis and you give it a Python file, and it will give you the bytecode representation just like if you're in there. So if you're ever interested and you're writing a script and you're like, what does this really do? Just load that out and start taking a look. It's not going to bite. It's not going to hurt you at all. So thank you guys for coming and letting me shout out you for about an hour and a half. Thank you so much for your questions. I've learned just as much from you guys as I hope you've learned from me. And I'll be around after for any questions if you'd like to talk to me anything. That's it.
Hand.
And can you keep that Python shell open? We're going to use you.
And we have two giveaways.
I always forget how it goes. So it's import random, right?
Yeah. Are you wanting to do an integer?
Integer, yeah.
I recommend random.randint.
Yeah, that's what we usually use.
This is from the Python conference. Never been used to the tag on it. It's an extra large, I believe. Sorry for
so
that.
So it fits everyone, if everyone can wear an extra large.
Yeah. Lots of choices.
Who has the number 34 on their badge? Anyone? So 33 is the highest?
I have 34.
You have 34? You have 35?
36. No, it's like 38, I think. We have 39 to not get correct. Here's the 39. All right, let's do 38 is the highest.
I was going to count all the way up.
Sorry to take the fun out of it, Walter.
All right, which is this one
so
for?
Maybe
or
you number 38 can tell me, does randint include?
First person gets
38 or does it exclude 38?
It includes.
Is it inclusive? Is this random? Okay, good. Just didn't want to leave 38 out.
Yeah. That's what Ferris told me last month.
Yeah, but you tried it the other way and it didn't work.
Oh, really?
So
yeah.
I recall.
So I was like, no, it's a half open interval.
All right, so you're ready?
Yeah, go ahead and hit it.
23.
That's me. Awesome. Pick your poison. Awesome. Oh, can you hold that up? Ferris got this for us. It's a signed copy of 2 scoops of Django 1.11.
I undersold it. I'm sorry.
You undersold it because
not that there's
left hand, right hand. Yeah. Cool. So this is for the short.
All right.
Okay.
Can't be 23.
36.
Nice.
Awesome.
Nice.
Even matches the shirt he has on now.
There you go. Perfect. Well, thanks everybody for coming out.
Yeah.
Thank you.
Thanks for hosting. Make sure you clean up after yourself.
Anyone is interested in presenting in future months, let us know. We will pass it on to Ferris.